Astronomers can now read alien skies like recipe cards. Atmospheres reveal whether distant planets might host living organisms. This video shows how we detect gases and what they mean. I'll explain the tools, their pitfalls, and surprising discoveries. By the end, you'll understand the clearest biosignatures to watch. A twilight of a distant world drifts across a star's face. An atmosphere is the thin shell of gases around a planet. It controls surface temperature, chemistry, and protection from radiation. Atmospheres also carry fingerprints, and those fingerprints hint at life. We care because gases reveal processes you cannot see directly. Telescopes collect starlight that passed through or bounced off that air. Spectrographs split that light into colors and show absorption lines. Those dark lines match specific molecules, like oxygen or methane. For example, Earth's atmosphere shows oxygen at 21%. So atmospheres are readable records and vital clues to life. A planet crossing its star makes a tiny, measurable dip in light. During that dip, some starlight filters through the planet's atmosphere. Molecules in the air absorb specific wavelengths, leaving dark fingerprints. Spectrographs measure those missing colors and infer atmospheric composition. This method is called transit spectroscopy, and it's widely used. Light passes through different altitudes, which affects absorption depth. Clouds complicate readings, and they can hide lower atmospheric layers. For instance, scientists detected sodium in hot Jupiter was P-96 billion. That detection used a 30-meter class telescope and precise spectrography. Transit spectroscopy reads layered signals and reveals atmospheric makeup. Some planets glow with infrared light and reveal heat patterns. Emission spectroscopy records that planetary glow directly, without starlight filtering. It matters because temperature profiles tell us about habitability zones. Radiative transfer models simulate how heat moves through gas layers. Observers compare models to spectra and extract temperature maps. For example, JWST detected methane in the atmosphere of was P-107 billion. That measurement used mid-infrared channels and complex retrieval algorithms. Emission spectra reveal both composition and climate signals on exoplanets. So emission measurements complement transit data and strengthen conclusions. Imagine a planet with oxygen floating in its sky, like Earth's. Oxygen is a strong biosignature on Earth, and it matters greatly. But oxygen can also accumulate without life through photodissociation. Familiar false positives include abiotic oxygen from water loss and C-otwo-photolysis. Methane paired with oxygen is a more persuasive combo and rarer. Detecting both requires high sensitivity and long observing campaigns. For instance, K2-18 billion showed water vapor signals over multiple transits. Those signals sparked debate, and teams still refine the data. So a biosignature is persuasive only with multiple, independent lines of evidence. Telescopes provide spectra, but turning spectra into gases is tricky. Retrieval algorithms compare observed spectra to many theoretical atmospheres. They vary parameters like temperature, composition, and cloud properties. Bayesian methods quantify uncertainties and show which molecules are plausible. Model degeneracies can mimic biosignatures and demand caution. Laboratory spectra and line lists improve confidence by refining molecular signatures. For example, updated methane line lists changed abundance estimates by a factor of 2, so retrievals give probabilities, not absolute proofs of life. Careful statistics and independent instruments strengthen claims robustly. Young planets often lose atmospheres to stellar winds and radiation. Escape changes composition over millions to billions of years. Hydrogen can escape, leaving heavier molecules behind and altering spectra. This matters because a present-day atmosphere may not reflect past habitability. For example, early Venus likely lost water and developed a dense C-otwo atmosphere. Atmospheric history therefore shapes where we should search for life, so we combine age estimates and stellar activity records to interpret spectra. That synthesis reduces false positives and highlights promising targets. In the next decade, telescopes will revolutionize atmospheric studies. Ground-based giants and space observatories will increase sensitivity dramatically. LUVOIR and HabEx concepts aim to image Earth-like planets directly. Direct imaging avoids transit geometry and captures reflected light spectra. Future instruments hope to detect oxygen, ozone, and seasonal changes. For instance, imaging could monitor seasonal methane pulses on a nearby planet. Those temporal signals provide stronger evidence for biological cycles, so next-generation observatories will move us closer to confident detections. We really can read alien skies like recipe cards today. Those atmospheric fingerprints tell stories about chemistry and processes. Some signals look promising, and others need more scrutiny. The science moves slowly, and that's a good thing. Slow progress ensures claims are robust and reproducible. Upcoming telescopes will expand our sample and reduce uncertainties. That means clearer biosignatures and fewer false positives. If we find life, it will change how we see ourselves. If we don't find life, we learn each planet's unique history. Either outcome teaches us about habitability across the galaxy. Thanks for staying curious and for following this cosmic detective story. If you enjoyed this, I can make deeper videos like this. If you'd like more deep dives, consider subscribing for gentle updates.